paper in your packet, hopefully close to where your homework was last night, that looks like this. Okay? So you are probably familiar with the idea of a dozen, where you've got 12 items. Have you heard of a baker's dozen before? 13. They give you an extra one. Like a lot of times during the summer, you'll get corn out of a corn stand, and they'll oftentimes give you 13 ears of corn instead of 12. They'll only charge you for 12, but they give you 13. That way, if there's like a worm in there, or somehow one of the corn ears doesn't, you don't feel like you've been cheated. Okay, so that's called a baker's dozen. That's what they used to do back in the days when you went and got all of your, bakery stuff. Like every day you would go to the bakery and grab stuff. Okay. The dozen kind of started out because it's easily divisible. Okay. If you have 2 people in your family, each person gets 6. If you have 3 people in the family, each person gets 4. If you've got 4 people in your family, each person gets 3. If you've got 6 people in your family, each person gets 2. Okay. And so that's why the dozen was kind of sold that way, because it was easily divisible among the household members, as opposed to like 10. It's like, yeah, somebody's getting shorted. Okay. If a teacher tells you to go and get a pack of paper out of the copy room for them, it's a big stack, it's a couple inches thick. It's bound in another sheet of paper. That's called a ream of paper. That's 500 sheets. So these are just ways that we can use to be able to tell you about different amounts. Okay. And I don't remember what a league is. I have to look that up every year. We're talking about sweetest day last hour. So a league is about 3.5 miles. So I just don't use that one very often, so I don't keep that in my mind.
So we can just write approximately 3 points.
Yeah, it's fine. I'm not going to quiz you on this, right? I'm just trying to get you to know that we oftentimes use terms to represent values. Okay? You've heard of 4.7 years ago. All that 4 would be 80 years. Okay? So we use these to represent things. Okay? The one that we use in chemistry all the time is called the mole. When we are counting things in chemistry, we are counting very tiny things like particles that we cannot see. So we use something called a mole to represent number of items. So it is 6.02 times 10 to the 23rd things. That could be atoms. It could be molecules. It could be people. It'd be a lot of people. Okay. But it could be paper clips. It could be anything. It's a counting unit. But we use it all the time in chemistry. The masses on your periodic table are in grams per mole. So if I want 1 mole of carbon, I'm going to take my balance and I'm going to measure out 12.0 grams of carbon. That's going to equal 1 mole. And I'm not going to sit there and count each atom 1, 2, 3, 4, all the way until I get up to this. Okay. I can just use my balance to get me there. If you had like a big thing of something and you knew that each gram was 100 items. Okay. So each one gram equaled 100 items. Okay. Would you need to count all the items, or could you just throw the whole container on a balance and get the mass of it? That balance reads 2.2 grams. How many items do you have in there then?
About 200 items.
Yeah.
A little over 200 items.
About 220 items in there. Right? Because 2.2 times 100 would be that. Does that make sense? So you don't actually have to sit there and count each individual item all the way up to 220. You just throw it on the balance, get the mass, and as long as you know this conversion, you're good. That makes sense? Well, your periodic table has all of those conversions for you. So for sulfur, it says 32.1. Okay, that means that for every 32.1 grams, I have that many atoms of sulfur. And I don't have to sit there and count out all of those items because you'd never be able to do it. They're too tiny to count, right? Okay. And we're going to get into all these different things that we use the mole for later on this year. Okay. So we abbreviate the mole as MOL. I know it saves us a lot of time, right? Just dropping that E off of there. Sometimes it's also a lowercase n. You'll occasionally, I don't know. Just yeah. I didn't make it up. I'm just telling you what it is. Okay. It's the amount of matter in a substance. We also call it Avogadro's number. And that's why back in October, you might have seen we celebrated Mole Day in AP Chem, October 23rd, 10 to the 23. That's how they came up with Mole Day. Okay, I know we're nerds. It's okay. We're fine with it. We've come to peace with it. All right, it's used to count extremely small particles like atoms or molecules. Again, you're not going to be able to sit there and count these out. It's just not going to work. Okay, you don't have that kind of time. So we just use a balance and work it out that way. All right. So we have a conversion factor. This is our conversion factor. So if we have 3.5 moles of sucrose, we can throw that into our dimensional analysis. We know that for every 1 mole of sucrose, we have this many molecules. Multiply across, and you've got your value right here. All right. This is also called the molar mass. Like your molar teeth in your mouth. Molar. Spelled the same way. The molar mass of any element to its atomic mass has the units on the periodic table. It's going to be in grams per mole. So manganese, if I look that up on my periodic table, manganese, not magnesium. Hopefully you guys have learned that lesson by now. You got probably dinged on that a couple times when you were 54.9. So this says 54.9 grams per mole on the periodic table. I just pulled that right off of my periodic table. So I'm going to set this up. Manganese. What's going to go on the top? Or what's going to go on the bottom? What am I getting rid of? So I'm going to put moles down here. I'm going to put grams up here. Wherever my grams are, that's where the number goes. Off the periodic table. And that's in every 1 mole. So then we just multiply across. 54.9 times 3. That ends up being 164.7 grams. This was off of my periodic table, so don't let that confuse you. I just grabbed that off the periodic table. So the answer is 164.7. Make sense?
Wouldn't you have to do sig figs on that one?
You want sig figs? Okay, I'll use sig figs. You're right. Good kid. There you go. Better? Better. My bad. All right, everybody happy? Okay. So here we are going grams to molecules. So I'm going to go 1.00 grams of water. I want to get rid of grams. Where do they go? Top or bottom? What's going to go on the other side for units?
Molecules?
I can't get into molecules. I don't have that
Oh, so
moles. Yep, I'm going to go moles here. I need to figure out the molecular mass of water. Okay, so we did that yesterday in class. I talked to you about molecular mass. We have our hydrogen and an oxygen. We have 2 hydrogens and 1 oxygen. I get the mass off the periodic table for hydrogen, which is 1, and I multiply across. I get the mass off the periodic table for oxygen, 16, multiply across. And then what do I do?
add them together.
Add. So this is 18.0. My units are grams per mole. So is the 18 going to go on the top line or the bottom line? The bottom. It always goes with the grams. And what goes on the top then? 1. So for every 18 grams of water, I have 1 mole. So if I wanted a mole of water, how much would I weigh out? 18 grams of water. Okay? Yep.
Is it always just like 1, or could you do like 1.0 or like?
It doesn't matter.
Because I don't know if you had to do like sig figs on that one, because you multiply.
But remember, these are conversion factors. This is coming off your periodic table. Conversion factors don't factor in to sig figs. It goes back to your measured amount. So your measured amount had 3 sig figs in it. That's how much your answer should have. So anything that goes in here that's going to be your conversion factors, they don't factor into sig figs. Remember that from beginning of the year now? Okay. So always go back to your measured amount. In fact, when I'm doing this in my calculator, I don't round for sig figs until the very, very end. So I keep everything in my calculator, and then at the very end, I do my rounding. Because with these fancy calculators, you can just go up and grab values and bring them down, and then you don't have to retype them in. So if you've got one of these fancier ones, let me know. I can also show you how to store Avogadro's number in here so you don't have to type it in every time. So if you're interested in that, let me know, and I can show you if you have one of these fancier ones. Okay, not right this second, but I'll show you. Okay, so I want to get this into molecules. I am not there yet. What am I going to get down here to get rid of? Moles. Do I have a conversion factor between moles and items or molecules? Yes, that is Avogadro's number. And for every one of these, I have 6.02 times 10 to the 23rd of these. And this right here, this number is the one that I will show you how to store in your calculator if you have a fancier one. Okay. So I'm going to go 1 times Avogadro's number divided by, on the bottom, if I have more than one thing down there, what would I need to do? I would need to have parentheses around everything, right? I'm going to hit divide, and then I'm going to put parentheses around all the bottom stuff. All right. My calculator then gives me 3.3444444. I could keep going all day, times 10 to the 22nd. I'm going to round this to 3 sig figs, which is going to be 3.44. And then I'm not going to forget to go back and grab those exponents off of the end. And that's going to be molecules of water. That's an E there. All right. Now, when you get to this point, look at your answer and see if it makes sense. Okay. If I have a gram of water, I can see a gram of water, right? Can you see a gram of water? Okay. People oftentimes forget to write this stuff down here, and they will literally give me this answer. Does it make sense that you would have 3.44 molecules in something that you could see with a visible eye? No. So at that point, if that's what you've written down, you've probably messed something up. So go back and you're not going to be able to double check your actual answer per se, but does it make rational sense? Okay. If you get to the end and you had a gram of water that you could see and you only had 3 molecules there, that doesn't make any sense, does it? Okay. So think about your answer. This happens every year. I'm telling you, every year. All right. That I think is easy. You can do that one. Okay. Atoms. I want to do this one. I want to do number 6. 6.02 times 10 to the 24th. This is going to be atoms of bismuth. All right. I want to get rid of what? Atoms. I'm going to take that into what? Moles. And I know for every 1 mole, I have how many atoms? Okay. There's a mole right up above Lynn and Ava there. See? If you forget the number, it's there. All right. Now I want to get rid of moles. And I can go to molecules. Or not molecules, atoms. My bad. Atoms. No, I don't want to do that. I just did that. I want to go the other way. I don't want to get into. I want to get into what? Grams. Yeah. That's mass in grams. Bad lippy. All right. Where am I going to get this from? Periodic table. So I'm going to look up bismuth. It is number 83. Its mass is 209.0. All right. Do you remember how to put this into your calculator? You should have an EE key there. For most of you, that's what I want you using. I want you to hit your 6.02, and I want you to hit however you activate that EE key, and then I want you to type in 24. Do not put in times 10 to the EE key does that. If you do that again, you will get the wrong answer. Okay? So this is what you're typing into your calculator. You're going to multiply that by the 209. You're going to hit the divide key. It's a good practice to be in after you hit that divide key, hitting a parentheses. Although if you hit the EE key, it's not going to matter on this one. But EE23, end parentheses, and hit your equals. What did you end up with? Did you get 2,090? Do I want to put a decimal here?
No.
No, because that would give me how many sig figs?
4.
And I only need
3.
And with this 0 being there, I just have 3 if I don't put a decimal.
Oh, grams.
Can't have naked numbers. I got to put their units on there. Don't want them running around naked. Get in trouble for that. That's some nudist colony. Come on, y'all. All right. How you feeling about that? Can I see your homework for tonight? Your homework. See your homework for tonight. I just want to see how far I need to go on this. Grams. Okay. Adams. Yep, there is an Adams one on there. I wanted to make sure. I wanted to see if I had one of those on there. Yeah, I want to do this one. All right. So we're going to skip to number 9. My answer keys for the notes have all of this stuff on there, I believe. So if you want to go back and work on some of these on your own independently, feel free to. Or if you have questions, we'll work through some more with you if you need it. Okay. So this is going to be grams of aluminum sulfate. And I want to get into atoms of oxygen. Okay, so this is going to be a 3-step conversion. We're going to have 3 different steps that we're going to have along the way to get to the answer. Okay, you ready? All right, the first thing I need to do is get rid of grams. Where am I going to go to get rid of these grams? Okay, I need to go into moles. Where am I going to get my numbers from then? Periodic table. Remember, this is in 1 mole. I'm going to get the values out of the periodic table. So aluminum is 27. 27 times 2 is 54. My sulfur is 32.1. So 3 sulfurs is going to give me 96.3. And then I need 12 oxygens. I can't do that in my head, you guys. Sorry. 32.1. Yeah, I got that right. So 16 times 12 is 192. I'm going to add all of these together. And that's going to give me 342.3. So that's the value that I'm putting down here for this first conversion factor. All right. Then I need to get rid of what? Moles. So I'm going to put moles on the bottom. And I'm going to go into what?
Wait, what? 342.3?
Yep. I had 54 from the sulfur. Or the aluminum, my bad. 27 for aluminum times 2. 27 times 2 is 54. My sulfurs, I had 3 of them because 1 times 3 is 3 at 32.1. That's going to give me 96.3. And then the oxygens are going to be 192. And if you add all that up, it should come up to 342.3. Yes? 9 and 6 is 5. Oh, no. No, 9, 8, 9, 10, 12. Yeah, it's 12. Carry the 1. 9 and 9 is 18. 19. So that's a 4. Carry the 1. Yeah. Yeah, that's what it ends up being. All right. Good. So I'm going to go moles into what? And this is where it's going to get a little difficult. Maybe.
Molecule?
Yes. Very good. Okay. So I have, this is the mass of all of this. Okay. So for example, let's say that I had a car. I had one car. So this is like one car here. And I wanted to know how many wheels we had and how much the wheels weighed. Okay. How many wheels do I have for every car? If you don't count the spare. 4. Okay. So that's what we're doing here. They're telling you this is the mass of all the cars. Now you got to figure out the mass of the wheels with all those cars. Okay. So we've got one of these. So 1 mole. In 1 mole, I have 6.02 times 10 to the 23rd molecules. They didn't want to know molecules. They wanted to know atoms. So for every molecule of Al2SO4 I have how many atoms of oxygen? How many atoms are in each one of these of oxygen? 12. I got that from the formula here for oxygen. Now, if they would have wanted to know sulfur instead of oxygen, what would this number have been? 3. If they would have wanted to know aluminum instead of oxygen, what would this number have been? 2. And that's the only difference between those problems. Okay, so let's calculate our answers here. So we've got 6.04 times Avogadro's number times 12 divided by our mass, which if you have a fancy calculator, remember you can just toggle up and hit enter and it'll pop that down into your equation so you don't have to retype it all, and hit equals. All right, I ended up with 1.27 times 10 to the 23rd atoms of oxygen. Now, if I would have just written this part down and ignored this, would that have made any sense at all? That I would have had less than 2 atoms in a 6-gram sample? Go back and double check your work. Does it make sense? Okay. Your moles will always be less than your grams. The only time that they're equal is when you're dealing with 1 hydrogen. Otherwise, it's always going to be less than every time. Okay. So keep that in mind. If they're asking you to do a problem, come on. Like this, your answer, they want you to determine the moles in this. Your answer will be a smaller number than this value, always. If you're going from grams to moles, it's always going to be smaller because your molecular mass is per mole, grams per mole. So keep that in mind. It's always going to be smaller. So it's a good way to kind of double check your work. Okay? Questions? All right. You need to have a pencil out, and that should be all you need. Oh, a calculator. You'll need a calculator. I needed a calculator for it, so I'm sure you will too. Not for all of it, but for some of it.